Hello everyone. Today I'll be guiding you through how computers protect information so it isn't changed by accident or on purpose, and how they make sure that messages come from the right person. We'll talk about three key digital security tools: hash functions, message authentication codes (MACs), and digital signatures. Think of them as digital fingerprints, stamps, and signatures that keep our online world safe and trustworthy. I'll make sure to explain each new word clearly along the way. Integrity and authentication. Before diving into the tools, let's understand two core security concepts. Integrity means that the data has not been altered during storage or transmission. Imagine writing a message to a friend. Integrity ensures no one has changed the words before it reaches to them. Authentication means providing who really sent the message. It's like signing your name so your friend knows it was truly you who sent it. Together, integrity and authentication build trust in digital communication. Without them, hackers could change information or impersonate someone else. These two ideas form the foundation for every secure system, from banking apps to government databases. Hash functions. The hash function is a mathematical process that turns any message, big or small, into a fixed length code called a hash value or digest. This code is unique to the message, just like a fingerprint is unique to a person. Key properties of hash functions. Deterministic. The same message always produces the same hash. Collision resistance. It's extremely difficult to find two different messages with the same hash. Pre-image resistance. You can't work backward from the hash to find the original message. Avalanche effect. A tiny change in the input makes a huge difference in the output. Common hash algorithms include SHA-256 and SHA-3. These are used in password storage, blockchain, file verification, and more. Now let's see how hash functions actually work. If you type the word hello, you get one hash, but if you change it to hello with a capital H, even though it looks similar, the hash becomes completely different. This drastic change is due to the avalanche effect in action. Why does it matter? It means that even a single character change in a file or message can be detected instantly. Hash functions act like tamper alarms for digital data. Real life users checking if downloaded files are original and unaltered, protecting stored passwords, detecting unauthorized file modifications. Message authentication codes, MACs. So while hash functions detect changes, they can't tell who made the change. That's where MACs come in. A MAC combines a message and a secret key to generate a code. Both the sender and the receiver share the secret key. When sending, the sender uses the key to create the MAC. When receiving, the receiver calculates the MAC using the same key. If both MACs match, the message is verified. This ensures both integrity, no tampering, and authentication, sent by someone who knows the secret key. MACs are used in network security protocols like TLS, banking systems, and secure communication apps. Hash-based message authentication, HMAC. This is an enhanced form of MAC that uses a hash function along with a secret key to make it stronger and much more efficient. Here's what happens. Number one, the message is mixed with the secret key in a specific way. Number two, a hash function like SHA-256 is applied. Number three, the output is HMAC. HMACs are resistant to common attacks and are used in APIs, online authentication system, and even IoT devices. Think of it as a double layer lock, one from hash and one from the secret key. Now let's talk about digital signatures. A digital signature is like a real world signature, but for digital messages or documents. It proves two things. One, the message came from the claim sender, which is authentication. Two, the message hasn't been modified since it was signed, which is integrity. How it works. The sender uses their private key. to create the digital signature. The receiver uses the sender's public key to verify it. This system is based on public key cryptography techniques, where everyone can know your public key, but only you have the private key. Digital signatures are legally recognized in many countries and are used in online contracts, government portals, and financial systems. Now let's see how digital signatures work. Number one, the sender generates a hash, digital fingerprint of the message. Number two, the sender encrypts this hash using the private key to create the digital signature. Number three, the sender sends both the message and the signature. Number four and five, the receiver uses the sender's public key to decrypt the signature. Number six, the receiver hashes the message again and compares it with the decrypted hash to check if it's authentic or not. If they match, the message is authentic and unchanged. Algorithms like RSA, DSA, and ECDSA are widely used and are popular ways to create and verify these signatures. Real world applications. Secure websites, HTTPS. Digital certificates and signatures confirm that you are talking to the real website and not an imposter. Software updates. Companies sign updates so your system can verify they haven't been tampered with. Cryptocurrency. Bitcoin and Ethereum use digital signatures to prove who owns what coins and who is authorized to make transactions. Messaging apps. Max and encryption protect your chat from hackers. Email verification. Signatures confirm that an email genuinely came from the claim sender. Security threats and best practices. Even strong security tools can fail if not used properly. Here's how to stay protected. Avoid outdated algorithms. Old hashes like 25 and SSH1 are weak and easily broken. Rotate keys regularly. Changing secret keys frequently limits damage if one gets leaked. Protect private keys. Store them in a hardware security modules, HSMs, or encrypted vaults. Use nonces or and timestamps. These prevent replay attacks where hackers reuse valid messages. Layer your security. Combine encryption, hashing, and signatures for maximum protection. By following these practices, we ensure that our digital data stays private, authentic, and tamper-proof, even in the face of sophisticated cyber threats. Thank you. That is it for today.